Oops. This is not the slide we need, but that's okay. So we left off on Monday talking about the Schrodinger wave equation. The Schrodinger equation is represented by this Greek letter psi, right? And it's a function of four quantum numbers, four variables. We talked a little bit when we did the Rydberg equation about the first quantum number, that first variable, n. And n, again, tells us the distance of an electron from a nucleus. Now, this is an average distance. It's not sort of an absolute value, as in the Bohr model of the atom. And so just taking a step back, the Bohr model said that, these energy levels were discrete, and we draw them as concentric rings, thinking that it's a certain distance from the nucleus that gives it that energy. In reality, it's a bit more, there's a lot more motion to an electron than just this particle moving around in an orbit. And so this is an average distance from the nucleus. When n equals 1, that first quantum number n equals 1, it's very close to the nucleus. As n gets larger, it's further away from the nucleus. Right? So again, we talked about this on Monday. Now, when we move on to the next quantum numbers, and as we move through these quantum numbers, they all relate to one another, and so they sort of build off of one another. The next quantum number, L, tells us something about the angular momentum of a particular electron. And so we call L the angular momentum quantum number. I'm going to be abbreviating quantum number Qn. And so it's kind of a script L, and so I write it, like a cursive L. And L is based on the possible values for n, and so L can be 0, 1, all the way up to n minus 1. Right? And so if n is equal to 1, what's the only value for L?
0.
Yeah, that's the only possible value for L is 0. If n equals 2, what are the possible values for L?
0 or 1.
Yeah, that's right, 0 or 1. Okay. And it goes on up like that for the different values of n. For each value of L, we call those different subshells. Right? So for n, let me just go back real quick. It describes the distance from the nucleus, and we call these shells. Okay. For L, we call these subshells. And these subshells have very particular names. If L equals 0, then we call it an S subshell. If L equals 1, it's a P subshell. If L is 2, it's a D subshell. And if it's 3, it's an F subshell. Now, right now, there are no naturally occurring elements that have electrons that have a L quantum number higher than 3. Now, you could excite, you could add energy into an atom and excite an electron up to a higher energy orbital, a higher energy subshell, but no known elements have electrons that naturally exist in a subshell higher than L equals 3. because they don't exist, there's not, we don't have particular names. These S, P, D, and F, they don't go in any real order. They're all based on German words for the shape of the path that the electrons take. So I don't even know off the top of my head what those words are. But if there were an L equals 4, we would call it a G subshell. And then we just go up in the alphabet from there. Okay. And so for n equals 1 and L equals 0, we'd call that a 1s subshell. Okay. For n equals 2 and L equals 0, that'd be a 2s subshell. For n equals 2 and L equals 1, that'd be a 2p subshell. Okay. And again, this is just helping us describe sort of the energy and the location of the electrons in an atom. Okay. All right, so we're going to move one step deeper into the wave equation and talk about M sub L. M sub L is the magnetic quantum number. It talks about the magnetic properties of the electron. And just like L depended on the value of N, M sub L depends on the value of L. And so M sub L can range from all the way from negative L through 0 up to positive L. And so M sub L has a lot more options than L does. So for L values, if L is 0, there's only one M sub L value. And it is
0.
That's it. If L is 1, what can our M sub L values be?
Maybe 1 or 0.
There's one more option. It could be 1, it could be 0, or it could be
-1.
-1. Yeah. So all the way from negative L through positive L. Okay. So if L is 1, we could have -1, 0, or +1. L equals 2, M sub L could be 2, 1, 0, -1, -2. When we talk about M sub L values, so we start with shells, and then we went to subshells. By the time we're to M sub L, we're talking about individual orbitals, okay? And so we call this, or we call these different orbitals. Perhaps that's a term that you remember from high school chemistry, right? S orbitals, P orbitals, D orbitals. And so if M sub L equals 0, well, let's say L equals 0 and M sub L equals 0, then we're in the we're in an S orbital. And because there's only one possible value of M sub L, there's only one S orbital, right? When L is 1, M sub L can be 1, 0, or -1. And so we call those p orbitals. And there's 3 p orbitals, right? There's only one s orbital, but there's 3 different p orbitals. They're associated with each value of M sub L. Sorry, I shifted these down a little bit. But for this last one, L equals 2, we call these d orbitals. And how many d orbitals are there?
5.
That's it, 5. 1 for each value of M sub L. Okay. The last number that we're going to talk about is m sub s. This is called the spin quantum number. And the spin quantum number tells us whether whether an electron is spinning clockwise or counterclockwise. And so whether or not that magnetic field that's generated by the spinning charge is pointing up. So if it's counterclockwise, this is the right-hand rule from physics. If it's counterclockwise, then that magnetic field is pointing up. If it's clockwise, that magnetic field is pointing down. We don't have to get into all that. We just need to know that the possible values for m sub s are plus a half if it's spin facing up, or minus a half if the spin is facing down. One of the ways that we kind of think about quantum numbers is by thinking about sort of seats in a stadium or something like that. If you're talking about where you're going to be in an arena, are you going to be in the lower bowl or the upper bowl, right? So that's our n value, close to the field or far away from the field. Then we go to which section are we going to be in, and so that's maybe like our L quantum number. And then once we go to L, then once we go to the section, then we need to know which row we're going to be in, right? So we're going to be in, say, row H or whatever. And that's like our m sub L quantum number. And then we need to know our actual seat number once we're in row H. And so that would be like our m sub S quantum number. And so with these four different quantum numbers, we're sort of specifying exactly a location within that atom, within those orbitals. I want to make it clear that we're not talking about an actual physical point in space, but rather a point in energy, if you want to think about it that way, for each of these electrons. And so these four quantum numbers describe completely the energy and the relative location of these electrons. When we talk about spin quantum numbers in particular, well, let me ask this question first. If we only have two values of m sub s, how many electrons could we have in each orbital, right? So let's say that L equals 0, sorry, let's say N equals 1, L equals 0, M sub L equals 0, M sub S equals plus 1/2. Okay, that describes a single electron. We need all four of those to describe an electron. And just as a brief recap, N describes our shell. We drill down a little bit. L describes our subshell. Drill down even further. M sub L describes our orbital. And we drill down even further. M sub S. Finally, we have enough information to actually describe individual electrons. And so if we come up with another set of quantum numbers, N equals 1, L equals 0, M sub L equals 0. Well, if I want to describe a different electron, I need to have a different set of quantum numbers, right? Just like in an arena, two people can't sit in the same seat. Two electrons can't have the same four quantum numbers. And so M sub S has to be -1/2. And so this is something called the Pauli exclusion principle. Don't say chemistry doesn't have any pep. This Pauli exclusion principle tells us that no two electrons can have the same four quantum numbers. right? Really, that means that no two electrons can have exactly the same energy and location within the atom. But in terms of quantum numbers, that means they can't have the same for quantum numbers, right? And so since we need 3 quantum numbers to explain or to define an orbital, that only leaves m sub s left over. And so since there's only 2 values of m sub s, this also tells us that each orbital can only hold 2 electrons. Right? Now it gets much messier trying to say how many electrons a subshell can hold because, you know, the s subshell only has 1 orbital, but the p subshell has 3 orbitals, and the d subshell has 5 orbitals. And so it's messier to try to make a definition like that for subshells. But for orbitals, we can certainly say each orbital can only have 2 electrons maximum. Right? Okay. So one last thing. Let me see. Yeah. One last thing for us to talk about in terms of quantum numbers. I have the wrong title on this slide. I don't want to talk about atomic orbitals yet. I want to talk about magnetic properties. If we have a set of electrons in a given atom, if each orbital is full, then there's an equal number of electrons with their spins pointing up as there are with their spins pointing down. Right? So let me put that in words here. For atoms with full subshells, there are an even number of spin up is what we call it if it's plus a half. So spin up and spin down electrons. Remember, spin up would be m sub s of plus a half. Spin down means m sub s is negative a half. And so let's take helium. Helium's an easy one. He's only got 2 electrons. But there's an even number, right? There's 1 spin up and 1 spin down. And so their magnetic fields cancel out. And so there's no magnetism there, overall magnetism. And so we say that an atom like helium, where each particle, each electron spin is matched or paired up, we say that those atoms are diamagnetic. Right? Diamagnetic. The way I remember this is that di means 2, right? That's our prefix for 2. And so that means that every spin is paired up. Right? And so if we have atoms without full subshells, there's an imbalance in the number of spins, right? Overall. Okay. So let's say we have sodium, for example. Sodium has 11 electrons. And so that means that sodium has 5 electrons with its spin, 5 electrons with its spin down and 6 electrons with a spin up. Okay. We'll talk about how I know that it's 5 down and 6 up tomorrow. But for now, you just need to know that they're not equal. And so overall, that atom has a tiny bit of magnetic field due to the fact that one of those electron spins is unpaired. When we talk about atoms like this, we say that these are paramagnetic. Okay. Paramagnetic means that there's some unpaired electrons. Diamagnetic means that all of our electrons are paired up in terms of their spin. Okay. All right. On our Moodle page is the link for today's class kick. Like I said, it's not a super long. It's not a super long activity. I'm going to put the link there. I'm going to go ahead and make us breakout rooms. And let you take a look at these problems. Again, it's not a very long assignment. And then the class kick, as usual, it saves automatically. So just make sure you have your answers in there by the time we're done with lab. Again, if you're having issues with internet on campus, maybe somebody who has a more stable connection can do the screen sharing today. If your group is having issues, do let me know. But we'll try to make it work as best we can. Okay. Once we get into rooms, I'll start popping around, see if anybody has any questions. So I'll see you all in a minute. Hello.
Hey, Dr. Davis. I think I might have the most stable internet, but for whatever reason, it won't let me screen share.
There were some students having an issue with that last time. See if you can do it now.
Yes, sir. Okay, it's showing up.
Okay.
Thank you.
Sure. Hello.
Hello. It's not letting me share my screen
Yeah,
because it's disabled.
I don't know why. That's not what I wanted to do. How about now?
He gave me the
Yes,
prompt.
it works now.
Yeah.
Okay, good.
Hey, Dr. Davis, I'm gonna have to leave the meeting.